Okay, this is an example of how you use the Sigma Zone Virtual Catapult Simulator to collect your data. So you will take the reading 5 times, but before you do that, you see these like question marks. This white one, if you drag that back and forth, you'll see the firing angle change, not the release angle. We want the firing angle set to 90 degrees all the way up as far as it can go. If you would like to change any of these settings, you may do so. Play around with it. You don't need to know what they do. It is not relative to what we want to be working on, right? So you could change those around if you would like. The other thing we want to make sure, this should be defaulted, but the ping pong ball should be all the way up at elevation 300. And you're just going to pull this all the way back, this arm back, until the release angle says 180 degrees, and then let go. It'll measure it for you. You can either measure from the back of the ping pong ball, the front, or the middle, but make sure that you're keeping that consistent whether you're going to be using it. I'm going to use, in this case, the bottom in the middle of it. So it looks like it's around 203. And I'm going to write that in my first reading, and then you can click fire again. Now, if you don't mess with any of the settings, it's going to give you the same reading each time. So I encourage you guys to mess around with the settings, but only these two. Don't change the firing angle and don't change the cup elevation. And we're going to release again to 180 degrees and let go. And now it says 210, so we're going to record that in reading 2 and fire again. Looks the same, 203. Oh, yeah, I didn't want to do that. Let's change something up. $250. And the last one, pull to 180 and release and measure. It looks like 208. So once you're done with that, you can kind of get rid of the Sigma Zone. We're not going to be using that anymore. And you're going to find the distance of your value averaged. So 203 plus 210 plus 203 plus 250 plus 208 divided by 5 to find the average is 214.8. I'm going to round this to 215. And then this is also the last important part that we need to know. Just for the purposes of getting nice numbers, we're going to divide this by 10. And we're going to use that distance in our calculation. So 215 divided by 10 is 21.5. And again, we're just going to round this to nice even 22. And this is the number we're going to be using. The zeros of your catapults when your catapult started, when we pulled back to release, and where your projectile landed. So if we kind of go back to this thing, it says, pull back the arm to launch, repeat 5 times. When you're calculating the zeros, use the following measurements. Where your catapult started, I'm going to give you that as 3 units. So that means that when you pull back that catapult, it's going to be 3 units. So on the x coordinate, that means our x is 3, and a definition of a 0 is when our y's are 0. And the other one, our y is going to be 0, and where our projectile landed was 22. So in this case, we have 22, 0. So use your zeros to create your factors. So there's a little bit of math involved here. So this is x is equal to 22, a negative 3, because our starting point is 0, and if we're pulling it back, that's a negative 3. So this is x is equal to negative 3. And what we want to do is kind of solve set it equal to 0. So if this is, if this is x is equal to -3, we want to add 3 to both sides to get this set equal to 0. And this is x plus 3 is equal to 0. This is factor number 1. And then if we have x is equal to 22, and that's a positive because it's a distance from our catapult in the positive direction, we're going to subtract 22 on both sides to get 0. X minus 22 is equal to 0. This is factor number 2. X minus 22. If we go back to our bottom sheet here, when calculating the y-intercept, I gave you that the height of the arm at the resting position is 3 units. So again, that was provided to you on that last sheet. Our y-intercept, by definition, is when x is equal to 0, right? And since our height is 3, our height is our y value, and I gave you that that was 3. So that is our y-intercept, 0, 3. Now to find the equation, you're just substituting in the factor 1 and factor 2 from above, right? So right now you have y is equal to -a, and we don't know what a is yet, times factor 1, which was x plus 3, and factor 2, which is x minus 22. And I don't want to put in an equation in standard form yet because we don't have it totally. So it says once we have our equation in standard form, we must solve for a. But we have too many variables involved here. We have an x, a y, and an a, right? So that's where our y-intercept comes into play. We're going to use our y-intercept and plug those numbers in for this equation. So y is equal to -a times x plus 3 times x minus 22. Well, I'm substituting x is 0 and y is 3 from our y-intercept. So 3 is equal to -a times 0 plus 3, 0 minus 22. And the nice thing about using the y-intercept is that since x is 0, it's nice and easy math here. We don't have to get big numbers. So 0 plus 3 is 3, 0 minus 22 is -22. If we are multiplying those together, 3 times -a times 3 times -22 is -66. 2 negatives make a positive, so this becomes 66a. And then using inverse operations, divide by 66 to get a is equal to 3 divided by -66 is going to simplify to 1/33. So that is our value of a. If I wanted to now write, using this equation again, right? Y is equal to -a is 1/33 times our factor 1 was x plus 3, our factor 2 is x minus 22. This would be our equation in standard form.